More than 60 years ago, when NASA first made plans to look for life on Mars, a British chemist named James Lovelock found himself often visiting the Jet Propulsion Laboratories as a consultant to a team, later to be led by that most able of space biologists, Norman Horowitz, whose main objective was to devise ways of detecting life on other planets. At the time, the planning of experiments was mostly based on the assumption that evidence for life on Mars would be much the same as for life on Earth. Thus, one proposed series of experiments involved in dispatching what was, in effect, an automated microbiological laboratory to sample the Martian soil and judge its suitability to support bacteria, fungi, or other microorganisms. Additional soil experiments were designed to test for chemicals whose presence would indicate life at work. Proteins, amino acids, and particularly optically active substances with the capacity that organic matter must twist a beam of polarized light in a counterclockwise direction. Soon, Lovelock started asking questions such as how can we be sure that the Martian way of life, if any, will reveal itself to tests based on Earth's lifestyle? And even more general ones like what is life and how should it be recognized? His colleagues asked him, well, what should you do instead? At the time, Lovelock could only reply, I'd look for an entropy reduction. See, during the past century, a few physicists such as Erwin Schrödinger, one of the founders of quantum mechanics, have tried to define life, and they all came to the same general conclusion. That life is a member of the class of phenomena which are open or continuous systems able to decrease their internal entropy at the expense of substances or free energy taken in from the environment and subsequently rejected in a degraded form. A rough paraphrase might be that life is one of those processes which are found whenever there is an abundant flow of energy. It is characterized by a tendency to shape or form itself as it consumes, but to do so, it must always excrete low-grade products to the surroundings. Yet, even if too broad and vague, this classification of life at least pointed Lovelock in the right direction. It suggested, for example, that there is a boundary or interface between the factory area, where the flow of energy or raw materials is put to work and entropy is consequently reduced, and the surrounding environment, which receives discarded waste products. It also suggests that lifelike processes require a flux of energy above some minimal value in order to get going and keep going. Planets enjoying a flux of free solar energy above these critical values would predictably have life, whereas those low on the scale, like the cold outer planets, would not. Assuming that life on any planet would be bound to use the fluid media, oceans, atmosphere, or both, as conveyor belts for raw materials and waste products, it occurred to Lovelock that some of the activity associated with concentrated entropy reduction within a living system might spill over into the conveyor belt regions and alter their composition. The atmosphere of a life-bearing planet would thus become recognizably different from that of a dead planet. Mars has no oceans. If life had established itself there, it would have to make use of the atmosphere or stagnate. Mars therefore seemed a suitable planet for a life detection exercise based on chemical analysis of the atmosphere. While Lovelock was thinking on these lines, Diane Hitchcock visited the Jet Propulsion Laboratories. The notion of life detection by atmospheric analysis appealed to her, and they began developing the idea together. Soon their results predicted that Mars is probably a lifeless planet. However, thinking about life on Mars gave Lovelock and later other scientists such as Lynn Margulis a fresh standpoint from which to consider life on Earth, and led them to formulate a new, or perhaps revive a very ancient concept of the relationship between the Earth and its biosphere. See, the only feasible explanation for the Earth's highly improbable atmosphere was that it was being manipulated on a day-to-day basis from the surface, and that the manipulator was life itself. The significant decrease in entropy, or as a chemist would put it, the persistent state of disequilibrium among the atmospheric gases, was on its own clear proof of life's activity. Take for example the simultaneous presence of methane and oxygen in our atmosphere. In sunlight, these two gases react chemically to give carbon dioxide and water vapor. The rate of this reaction is such that to sustain the amount of methane always present in the air, at least 500 million tons of this gas must be introduced into the atmosphere yearly. In addition, there must be some means of replacing the oxygen used up in oxidizing methane, and this requires a production of at least twice as much oxygen as methane. Back then, most geochemists regarded the atmosphere as an end product of planetary outgassing and held that subsequent reactions by abiological processes had determined its present state. Life merely borrowed gases from the atmosphere and returned them unchanged. The contrasting view here required an atmosphere which was a dynamic extension of the biosphere itself. It wasn't so easy for Lovelock and Hitchcock to find a journal prepared to publish such radical a notion, but after several rejections, they found an editor prepared to publish it in his journal. This was Carl Sagan. It was a long way from a plausible life detection experiment to the hypothesis that the Earth's atmosphere is actively maintained and regulated by life on the surface. However, the climate and the chemical properties of the Earth, now and throughout its history, seem always to have been optimal for life. For this to have happened by chance is unlikely. By then, a planet-sized entity, albeit hypothetical, had been born, with properties which could not be predicted from the sum of its parts. It needed a name. Fortunately, the author William Golding was a fellow villager of Lovelock. Without hesitation, he recommended him that this creature be called Gaia, after the Greek earth goddess also called Ge. What back then emerged as the Gaia hypothesis has by now come to be referred to as simply the Gaia Theory. The cosmic cycle of life and death, stars being born and reborn, gravity densely packing matter to be fused and new elements to be created. Soon our planet Earth formed. It consisted of a solid, liquid and gas layers, which were composed of a variety of different elements, some with the capacity to form complex organic molecules, which could then dissolve in the primordial sea. Let's now try a little thought experiment, shall we? Imagine that the whole Earth is made up of all the parts needed to assemble a watch. An astronomical being then takes this Earth and shakes it. Any single watch part, swirling and moving up and around in an endless sea of other watch parts, by a way of random forces, has a non-zero probability that it could assemble into something that looks like a watch. In the same way, out of combinatorial chemistry and simply salt water, one could see how it is possible for a simple lifelike task to have emerged. The accumulation of such proto-life must have eventually led to the first microorganism, capable of using sunlight and the molecules of the environment to produce its own duplicate. From this first organism sprung a sea of many others, some with the ability to harvest sunlight and some without. Those that couldn't sat on top of what is now a long food chain, powered by those that could. At the present time, the composition of the Earth has come to consist of the following. The distinguished Swedish chemist Silen was the first to calculate what would be the result of bringing all substances of the Earth to thermodynamic equilibrium. Here is the result. In reality, this world is an imaginary one, as it precludes the constant flux of solar radiation, which is the driving cause of flowing water, winds, and other thermodynamic disequilibria. Instead, we might want to imagine, as Lovelock did, a lifeless steady-state world, one where substances are brought merely to a chemical equilibrium, a state where the rate of forward and reverse reactions tend to equal each other. Here's the results of the calculations performed for the atmosphere. In a relatively short amount of time, the composition of the atmosphere would seem very different from that of today. Moreover, fossil fuel records show that life has been around way longer than it takes for these reactions to occur, and that they really couldn't have occurred, as this would have been the death of life. Here we catch our first glimpse of Gaia. A complex entity involving the Earth's biosphere, atmosphere, oceans and soil, the totality constituting a feedback or cybernetic system which seeks an optimal physical and chemical environment for life on this planet. The maintenance of relatively constant conditions by active control may be conveniently described by the term homeostasis. In the 1940s, the American mathematician Norbert Wiener defined the new science of cybernetics as the study of control and communication in machines and living things. Cybernetics is a whole science on its own, but one of the most important contributions it made was in our understanding of feedback. For example, whenever you walk in an upright position, you are using multiple feedback mechanisms to do so. As you take a step forward, random disturbances from the environment would cause you to wiggle and fall. For this to be prevented, you have to counteract any force which causes you to stray away from your optimal position. The optimal position then results from the vector sum of all the forces and counterforces. To get a more rigorous understanding of this mechanism, we shall consider the thermostat. With a thermostat, the optimal temperature for a system is measured against the output temperature of that system, and the difference is subtracted, in the case of negative feedback, from the input. This difference could be thought of as an error signal which propagates backwards, adjusting the parameters of the controlled system, in this case the temperature. A more general term for this type of system, and one which is independent of the variable that is controlled, is a homeostat. Your body is a multivariable homeostat. It consists of many different parameters that need to be kept at relatively constant values, including temperature. Gaia too has its own homeostatic mechanisms employed in the regulation of things such as oxygen levels in the atmosphere, salinity in the sea, and even the global surface temperature. The stability of the atmosphere on Earth is not a consequence of chemical equilibrium like on planets without life. All the atmospheric gases, other than the noble gases, are either made by organisms or processed by them. Take for example oxygen. It is convenient for chemistry to express the oxidation power of an environment in terms of its reduction oxidation or redox potential, measured electrically and expressed in volts. It is in fact no more than the voltage of a hypothetical battery with one electrode in the oxygen and the other in the food. Nearly all the oxygen produced by photosynthesis in green plants and algae is cycled through the atmosphere and used up in that other fundamental activity of life, respiration. Reacting with oxygen is combusting. Anywhere one might light a fire and measure the released energy to quantify the concentration of oxygen in the air. On Earth, this concentration is actively maintained by life to provide optimal conditions for life. Similarly, carbon dioxide as a greenhouse gas released in the respiration process is also actively maintained in order to regulate the global surface temperature of the planet. Since life started on Earth, the energy provided by the Sun has increased by 25 to 30%. However, the surface temperature of the planet has remained within the levels of habitability, reaching quite regular low and high margins. The reason for this is that the flow of carbon dioxide from the atmosphere to the soil is regulated with the help of living beings. When CO2 levels rise in the atmosphere, the temperature increases and plants grow. This growth brings higher consumption of CO2 by the plants, who process it into the soil, removing it from the atmosphere. Drawing from areas such as chemical oceanography and marine biology, the Gaia theory also involves feedback loops used for regulating the salinity of the sea. To understand how, one has to consider the osmotic pressure or the difference between internal and external salinities within organisms in conjunction with a negative feedback which can keep this difference within a desirable limit. Ocean salinity has been constant at about 3.4% for a very long time, which is convenient as most cells require a rather constant salinity and do not generally tolerate values above 5%. River salts, among other things, should have raised the ocean salinity much higher than observed. However, the composition of the seawater is far from equilibrium, and it is difficult to explain this fact without the influence of organic processes. One suggested explanation lies in the formation of salt plains throughout Earth's history. It is hypothesized that these are created by bacteria colonies that fix ions and heavy metals during life processes. When the Industrial Revolution arrived in Britain in the 17th century, people had no notion of what they were doing when they started releasing all of these greenhouse gases into the atmosphere. By now, the level of carbon dioxide has increased by 50% and the global temperature has increased by 1.1 degrees Celsius. One, however, should not overlook the fact that the consequences of air pollution would be incomplete and probably ineffectual if the possibility of a response or an adaptation by the biosphere was overlooked. The very concept of pollution is anthropocentric, and it may even be relevant in the Gaian context. Many so-called pollutants are naturally present, and it becomes exceedingly difficult to know at what level the appellation pollutant may be justified. Carbon monoxide, for example, which is poisonous to us and to most large mammals, is a product of incomplete combustion, a toxic agent from exhaust gases of cars, coke or coal-burning stoves, or cigarettes. A pollutant put into otherwise clean fresh air by man, you might think. However, if the air is analyzed, we find that carbon monoxide gas is to be found everywhere. It comes from the oxidation of methane gas in the atmosphere itself, and as much as 1,000 million tons of it are so produced each year. It is thus an indirect but natural vegetable product and is also found in the swim bladders of many sea creatures. Almost every pollutant has, to some extent, large or small, a natural background. Despite this, for each of our actions there are only consequences, and the increase in surface temperature might result in changes which are not in our benefit. James Lovelock's work was highly involved in the problems of pollution, and has since inspired an environmental political movement and the general goal towards a sustainable economy, represented by the shift towards electric vehicles and renewable energy sources. Modern ontogeny, the study of the development of the organism, tells us that your body is made up of cells, and that all of these cells are the progeny of a single cell, the zygote. Similarly, phylogeny, the study of the evolution of the race, tells us that all living things on Earth originated from a single common ancestor, a single cell. This was Luca, the last universal common ancestor. One might then wonder, is it possible to view all of phylogeny, the entire history of life on Earth, as the developmental biology of Luca, and consequently the entire biosphere, the whole of living matter, as the body of Luca? But not a passive body, no. Instead, an active agent itself, an entity, capable of adapting the material environment to itself, and at the same time be adapted by this very same environment, with whom they together form a single, self-organizing system.